Right, hello. So I'm Natalia, and yes, just a little bit about me, because I'm a developer. I'm at Erlang Solutions, and I specialize in fintech, right? So that's a little bit strange why I'm talking about robotics today. The reason is that in my previous life, I was in academia. In academia, I was a PhD student, I was a postdoc, I was a lecturer. And there, my research interests were distributed systems and robotics. And so that's love and passion. They just continue with me. Unfortunately, I'm not very much involved in this at the moment, but I will share with you all the love and all the passion and all my knowledge about the robotics and functional programming. Who am I as well? So I'm a chair of the embedded working group that's in the Erlang Ecosystem Foundation. Does anybody know about Erlang Ecosystem Foundation? Yay, fantastic, a few. So essentially, it's a foundation for Erlang community and it supports, and if you write anything in Erlang, Elixir or any other Beam language, and you have something interesting, but you need a bit of funding, that Erlang System Foundation will support you. And then it's a community of like-minded people who are very interested, very passionate about Erlang and Beam languages, so do join. I'm sure you will enjoy it. And also, I'm a steering committee member of the Erlang workshop. That's an academic workshop. But if you have anything that you can publish, you're interested, that's also a venue for you. A bit of a disclaimer. I did my best to do the research, and what I will be talking about is based on my own experience in the papers and information available on Google Scholar, also from talking to people, but still, it's my opinion, it's what I found. So if you know something to share with me, I'll really appreciate sort of knowing a little bit more about robotics and functional programming. Right, so let's start with actual which languages are used in robotics. So the only one I found was actually Lisp, and it's in Roomba. So the information comes from 2021. It's on this hacker website. And there is a rumor that it's not used that much anymore now. I don't know whether it's true or not. I don't have inside information from there. But yeah, and the reason for that is that the company was developed and sort of grew out of an idea from MIT. And actually the idea came from 1989. Can you believe that? They had an idea about Roomba in 1989, and only in 2002 it was bought by iRobot, and they developed Roomba. That's fascinating. So then we go to actual frameworks developed in function languages. The most popular of them is Yampa, and quite a lot of used until 2008. Another one was Fren, also a Haskell one. It seems to be the one that most influential. So people, when they talk about frameworks in robotics frameworks in Haskell in particular, they always talk about Fren. There was Frop, also Haskell, and those from Erlang community may know Erlang framework, robotic framework. But they all sort of stop existence by 2008. Any sense why that happened? Something else? Yes? Anybody?
Actually collapsed.
Well, probably, but something else happened. It was actually ROS, Robot Operating System. We'll talk about a little bit about it. But in 2007, ROS was introduced, and then it sort of killed all other initiatives. And from the current one, outside sort of for functional programming, there is ROSiE. And ROSiE is ROS Integrating Erlang, and it's very close to my heart, and we'll talk about it. But the thing is, I know about ROSiE because I love it, and I'm the one who sort of started it, but I'm not sure how many people know about it. And here, the question is, maybe there are more, but people just don't know it because it's not publicized. So for now, it's just ROSiE. So what I didn't take into account are educational tools. So there are quite a number of them for Haskell, for other languages, and these are sort of to teach people in a fun way programming. And functional programming like Erlang, Haskell, Lisp, or Camel, they seem to be a good way to do that. And there are quite a number of them. And another one was quite a number of researchers' evaluation of suitability. So people say, yes, functional programming, it's so amazing, it's so good, let's try it in robotics, for example. And people try, and they say, yeah, that seems to be good, and that doesn't go much anywhere. But then we have lots of research and sort of development of functional languages in IoT. So then the question is, why do we have so much functional programming in IoT and we don't have that in robotics? And actually, that's what the rest of the talk will be about. We'll talk about the reasons why we don't see much of the functional programming in robotics, and then we'll also talk about ROSiE. So first of all is ROS operating system. So it happened in 2007. An idea behind it was that no lab, no institute is capable to do anything in robotics alone. So they needed a community, and Open Source Robotics Foundation was founded and ROS was developed. And so what it provides are tools, libraries, and conventions. So it's not actually an operating system as it is, it's actually a framework. And the idea behind that is people develop elements from all over the world and they contribute, and it's open source. And then, for example, if you need, if you're interested in exploring sort of room mapping, for example, right? But what you need motions. You need robot to move, you need camera, and only after that you can actually start mapping the room. So the idea is that people who are interested in motion and people who are interested in camera connections, they write those things, they put it open source, and then you can focus on actually mapping things. And maybe you use some libraries already developed and you build on that and you release it as open source and become exciting, interesting, and that's how sort of the whole robotics things moves. And it's multi-language, but the main languages are Python and C++. These are the languages. So what's about ROS? ROS is open source, and this is sort of a structure, a simple structure that we can observe. So it is distributed. We can have it on different machines. We have nodes, and they're responsible for some kind of functions. Then we connect them. And then we have a ROS master. And there, as a person interested in distributed system, this becomes interesting. So this ROS master, it actually monitors what's happening around. And if you want to be known to this particular robot, your node needs to be registered with ROS master. If ROS master doesn't know about a particular node, that node is not taken account, it's not part of the robot. The way that nodes communicate with each other is publish, subscribe. And as I said, ROS master needs to register everything. And the end of support is 2025. So yeah, it's sort of dying, as you can guess. But then in 2015, there was another initiative started, and this is ROS 2. So when you saw on the previous sort of picture, and that's what started my interest in ROS, is that we have ROS master and we need to register everything in there. And if you're interested in distributed system, of course, you know this is a single point of failure. So ROS node fails, and that's it. Nothing happens. It's also not fault tolerant, because if we sort of disconnect, or there is no elasticity, we want to add something, etc., until you update the ROS nodes, nothing will happen. And that's what drew my interest to it. In 2015, they started developing another idea, because they also noted that something is wrong with ROS master and wanted eradicated. There were some other things that they changed, but these are what two sort of main things they wanted to change there. the data distribution, so now we don't need a ROS master to register everything there. We now can have a peer-to-peer connections, and it's based on DDS. This is Data Distribution Service. And the problem that occurred then is that it's actually not that simple to move from ROS to ROS2. And initially, the uptake of ROS2 was really slow. And actually, as you can see, there are companies that specialize in moving from ROS to ROS2. And from thinking that there are companies, you already can imagine that it's not a simple task. So you can't just migrate. You can use sort of some of your libraries, but it's not that simple. You actually need to be very careful. And the larger system you have, the more difficult it is to do. And initially, companies actually, and lots of research didn't want to move on, right? When you have lots and lots of things and it works, why would you move? And ROS2 is sort of just started. But Robotics Foundation is really determined that they need to move. We need to move to something better, something faster, something more modern. So they sort of pushed all their weight behind ROS2, and ROS2 is now sort of living, thriving, and ROS2 is getting out. So that's the first reason. There was ROS that lots and lots of roboticists started contributing to, and now maintaining any functional programming framework for robotics, it's just not feasible. You can't compete with them anymore. So that's the reason the sort of those frameworks that existed before 2007, they sort of started dying out and they died. Right. The second reason I think that we don't see much is there are lots and lots of advancement, research, software, which is proprietary, and we don't see it. We don't know that it exists, right? So people don't talk about it. I think for those of you who sort of work with, especially I think in academia, it's really, because when we work in the industry, we sort of know, oh, those use it, the language, and thus we sort of have rumors. In academia, it's much more difficult to pinpoint who uses which languages. So I think that's partially the same thing. We just don't know because the code is closed and we don't know which languages they use. And the third reason, I think, is the difficulty of communicating between robotics and computing. And I think it's really, really difficult for developers, for computing scientists to enter robotics. And the reason is that the fields are very mature. Well, not as mature as chemistry, physics, and other areas, but in comparison to each other, robotics and computing are mature. It's not like IoT that was developed much later, right? And we sort of, when we go, computing goes into IoT, then, well, it's new. Nobody knows anything about it. So, and we don't know. So that's exciting, right? And we bring new things there. That's fantastic. But robotics, it was developed in parallel. There is lots of knowledge. There is language there. And it has its own vocabulary. So, for example, when we talk about safety, right? In computing, when we talk about safety, we probably talk about cybersecurity, right? Or we can safely fail, something like that, right? So we are notified that there is a failure there. Whereas in robotics, safety is very much human and robot interaction. And if you say it's safe, it means a robot can safely work with a human and it won't hurt it. So, for example, imagine you're talking to a roboticist and you say, my idea is completely safe. And you just mean that it's cybersecurity safe. And then, of course, they look at you and they say, you have no idea what you're talking about. Right? Have you even tried it? How do you know? There are a huge list of standards that you need to follow. How do you know that it's safe? Another one is fault tolerance. And in computing, fault tolerance for us, I think it's very much about it failed, it automatically recovered, and where sort of there is no human interaction is there. That's fault tolerance. But in robotics, fault tolerance actually meant it failed, but the robot's still working and it's intact. So imagine you have a drone and it flied and something failed. So for that drone, that it's fault tolerant, it means that it continues flying, safely lands, and the robot is still a robot, not sort of a pile of metal. So these are very different concepts, right? And when we say your robot is not fault tolerant, obviously you will have lots and lots of opinions about your knowledge in robotics from roboticists, because the same word means very different things. You are right, the robots are not fault tolerant, but they are not fault tolerant in the different aspect that one roboticist think. So here I'll be talking about my own experience as well. So when I started working with robots, I was pretty sort of confident, again, that, you know, the robots are not good and we can fix them. But one of the things that you sort of need to keep in mind when starting working with robots is that they're absolutely different. The hardware is very different from what we got used to in computing. And the first thing is wireless. Connection is mainly wireless and less stable. So when we write our software, we mainly think that it's either online or offline, right? We're rarely writing software that can do both, right? Then waits when it's online, then it does something, and then waits when it's online. We mainly write this either online or offline. And a good example, I think, to appreciating that are UK train lines. If you ever tried to walk on a UK train, you would really appreciate the difference between online and offline. Because you get on the train, you're very enthusiastic, you're on the station, you get connected, everything works. The train started moving, that's it, you're offline. Good luck. Until the next station, maybe. Then we work with limited computation resources. Again, we may think about mobile phones, but the majority of the time, we don't write even for mobile phones, we don't write that extensive application. And we don't need to think that much about computation resources. I'm coming from distributed systems and working with servers, right? So I completely didn't think about how much, well, I thought how much resources I have, but usually when you think about sort of processing power, you think about like 600 or 1,000 cores, for example, this kind of numbers. And of course, you're not thinking that this computation power is not enough. It's more about how you utilize it. Whereas in robotics, you actually need to think about it. Limited power resources, again, that's a huge thing. For example, when we started doing experiments and just trying our ideas, the really frustrating thing was the battery dying. So imagine you're in the middle of an experiment and you're really looking forward to it, and it's just a bit bigger than you used to. You leave it and you wait it, maybe you leave it overnight, then it's not that frustrating. But imagine waiting the whole day, and then when it's just about to finish, your battery is flat, that's it. Try again. Right? Really, really frustrating. Environment needs to be taken into account. So we're used to that our computers are sort of protected. If it's a mobile phone, that's the user's responsibility to take care of it. Just don't drop it in the water, right? Don't take it for swimming. That's it. That's what we expect. The camera is sort of brand new, something will clean it. Take the photo from under something. It's the user problem that something might happen with the device and the user should do something. Well, with robots, we need, well, that's the reality. That's what we work with, right? And these kind of things also need to be taken into account. Then the last one is a single robot can be a network of devices. And maybe your computation is not the most intense, the one that uses the computation. So you can optimize it as much as you want, but there is a motion next to you that uses all the power, and they use it all, and you have nothing for computation. Sad story. So when you're going into robotics, we actually need to think about all those things. And that's what we are facing when we are just entering it, right? We think, okay, we are going to work with robotics. We're going to run some kind of experiments. And before we run, we plan, and we think that we're going to do this and that. These are actually all the obstacles that we need to go through to reach to some kind of initial investigation that we want to do. While getting ready to this talk, I found this paper, How a Functional Programmer Would Be Received by Artists. And I saw similar papers about how functional programming will, fit not artists but roboticists and everything. And it's really interesting here, the conclusion, and it sort of struck me, but it struck me only after I've been through the journey myself, that artists and roboticists, they don't care about functional programming. They don't care how beautiful it is. What they care is art and robots. And it seems so simple, but I think us being sort of fascinating, how functional programming is amazing and how it helps us to solve this and that problem and how it should be used by everybody, we forget that actually it's our passion and they have their own passion. They're not interested in our functional programming. They're interested in robot moving, or they're interested in hand grabbing something really nicely and putting it back. And I think behind it is a really, really deep thought in that, yes, functional programming is amazing, but in making their life easy without sort of focusing very much on functional programming. We can talk about how amazing it is between us, but to other sort of people, it's all about productivity, and they don't care that much about it. And the lesson that we learned here is that API is the must. So if you're developing something for somebody, make sure that their interaction with what you developed remains the same. So if they used to program Python, it should remain Python, because they're not going to use Erlang, Scala, or Haskell just to get a better speed up, for example, in their robots. They're not. But if we want them to use, if we want them to enjoy it, we need to develop tools for them being able to do that. Right, and another reason it's so difficult is that when we do something, we need to develop a demonstration. And developing a demonstration in robotics is really difficult even with ROS. It requires lots of time. So first of all, it's difficult. It's a new one. We need to pick those things. We need to start to developing. We need to start putting them together. But it's another thing is about understanding what exactly happening there and be able to say that something is better than the other. From my personal experience, what we wanted to do, we wanted to have a set of robots, and they would follow each other. And the first one would follow human, and then how they would interact with each other, right? So it's a face recognition, it's pretty simple, all the bits and bobs are there. So you can think of a human just walking, and behind you have a trail of robots that just follow you very nicely. Very nice, seems to be very simple from robotics perspective, demonstration with which we can demonstrate some properties and use of Erlang, for example, or any language that you want. And this is what we ended up doing, right? So these are robots that we used, and this is sort of car, those with the Raspberry Pi robots. And we thought they would follow a human, and so that we will sort of demonstrate. But then when we started doing it, we realized that we don't understand what's going inside there. And we were sort of simplifying it, and then simplifying again, and simplifying again. So what we simplified to was those Raspberry Pis connected, wired, connected to the socket, not on the battery, sending echo messages to each other. Can you imagine that? Starting with a simple sort of demo, going back to echo messages to each other, just to understand what's going on there. And the reason I'm talking and giving this example is that we're using, so Raspberry Pis have been used a lot, right? But this is a new sort of area that we're using it. This is a very different, very established software that we want to sort of integrate. And we do need to make sure that we understand about the processes that's going on. So when I go simple, it's just basic simple. Just make sure that you understand everything on every stage. So what to do? Well, first of all, I think if you're interested in working with robots, be prepared that there will be misunderstanding in the languages. That with roboticists we use the same language, the same words, but those words have very different meaning. So my suggestion is if you sort of pitch your idea constantly all the time, just write down the words that you are constantly using, explaining your ideas, then go to Google Scholar, type robot, type your words, and read the papers and sort of learn what roboticists mean by those words. The other one is going a lot to the conferences. So say it's robotics, go a lot to robotics conferences, talking to people, listen to the talks, see the language, see their concerns, what they're talking about. Do what you want to do. So if it's a research proposal, if it's an idea, if it's something, just pitch it, go for it. Be prepared that you will get a feedback, and this feedback might be really rude. Like really rude. I think in academia we sort of got used to getting feedback that your idea is not good enough, it won't work, or something like that. And it's sort of unpleasant. But here, because moving to a new sort of area, it can be as basic as you understand nothing. You have no idea. It's just so dumb and things like that. So it can be really rude, but don't get discouraged. It all comes to misunderstanding. Just use the feedback and try again. So that's sort of the end of the first part about the reasons that I think we have so little functional programming, why it's so difficult to move into the area. And I will talk a little bit about ROSiE. So ROSiE is ROS operating system integrating Erlang. And to me, it started in 2015. I was a postdoc at Glasgow University. I had 2 years funding when I could do what I wanted. And then I thought, well, what I love robotics, and I would love to try working with it, because before I never worked with this, and we had a lab, and I had quite a number of robots, and I thought, I want to have my own robots. I want sort of a collection of them. I wanted a cooperative robots, so robots that work with each other, they collaborate. I worked with Erlang, so I thought I wanted them to talk using Erlang, fault tolerantly, reliably, connection lost, connection gained again, life is good. I wanted them to scale. I wanted to have many complex robots, like thousands of those, and do something. Yeah, that was the idea. So first, let's start with the cooperative robots. Cooperative robots, they have quite a number of different, just to explain what I mean here. So when we think about many robots, we think about swarm robotics. But swarm robotics is very different. And then usually we have these teeny tiny devices. And the behavior, something that we see, it emerges from collection of them. So behavior of which one can be really tiny, like move left, move right, something blinking or something like really, really basic, really simple. And then when there are so many of them, like thousands, then we see something interesting coming out of it. Whereas I was interested in actually cooperative robotics. So each robot is a complex device in itself. And then each robot can do something independently, and then we have many of those robots doing something together. So, for example, one of them is digging, another one is bringing, a bucket, another one sort of filling it, so they all do something nicely together. Right. And the areas was that they can be similar architecture, but that's the easiest example. They can be of different architecture, and then also human interaction with a human. But here, when we talk about, my main focus was on communication, and it's not like robot-human interaction. It's more on a sort of signal level that humans don't understand. Yes, and the main reason that sort of brought me in here was this diagram showing sort of robots, nodes, and different nodes, and then they need to communicate with each other, and then have this common single node which is main sort of single point of failure. Then in 2015, 2019, we did a sort of preliminary research. If you're interested in that, there are quite a number of talks on that, what we did, and sort of gaining knowledge, exploring, getting information there. Then in 2020, together with Laura Castro, we sort of led an EU proposal. It was for 3 million. We got really, really lovely scores, but we didn't get the money. And for those of you writing EU proposals, you know that really nice scores are not good enough. They need to be perfect. And then I left academia. But then we collaborated, thanks to Erlang Ecosystem Foundation, we collaborated with Milan University, and we had a fantastic student there, who's not a student, of course, anymore. He's a really nice developer. And Piotr Gzinger, and we collaborated in developing the first version of ROSiE. And but here what we did, we didn't use ROS, we used ROS2 here because it was gaining popularity, so we thought we'll go for ROS2. And here, what he did DDS implementation. DDS stands for, it's here, Data Distribution Service, implemented in Erlang. And then the two main things that we wanted to make sure that we have there was interoperability. So we wanted to make sure that our ROS2 nodes communicate with ROSiE. And also in ROSiE, we can use nodes from ROS2. So the initial idea that we're not going to develop any sort of new in robotics. There is roboticists for that, but we enable the communication that Erlang is really good at. And the second one is the sort of feature of Erlang is a hot code swapping, and we wanted to keep it. Just to give you an idea, so what's happening here, on top we have this our user application, and beneath it, that's ROS2, and beneath it we have different implementations, right? RCL stands for Robot Client Library. So Robot Client Library, it's sort of RCL is for the main part, and then we can have sort of differences in Python and C. And then beneath it we have sort of middle interface to allow us to work with the communication. And then there are different actually implementations of DDS. So there are different versions. Because in itself, DDS is just a protocol. I'll talk probably better here. So DDS in itself is just a networking middleware specification. So it's not just implementation, it's just a huge thing that describes how you should communicate with each other. And it actually is a fantastic thing because there are different implementations for that, but the main point that whichever sort of DDS you implement in whichever language and how you implement it, all sort of, well, in this case, ROS2 nodes that use DDS, they all can communicate with each other. That's the sort of beauty of that. And that's how sort of subscription goes on, is that we have a topic, and then we do the readers and writers, subscribers and readers. So we can write to different topics, and we can read from different topics. So that's... So what Luca did is that everything was written in Erlang now. So now we can write our application in Erlang, but we also can use existing applications written in Python or ROS or whatever. Then we have our ROSiE ROS client library. And because at the moment we only have Erlang, we sort of combined those two layers together. Then DDS was implemented in Erlang, and then it all sits on the VM. That's fantastic. Right, so this is a ROSiE logo that Luca came up with. And what it gives us is that we have this interaction between ROS and ROS2. So if you have a ROS2 robot, then it can communicate with a robot working in written in Erlang, so ROSiE one. Or a ROSiE can actually use different existing sort of libraries that written in different languages, or you can write something in Erlang if that fancies you. And this is how sort of Luca demonstrated it. So we have our implementation, and then he sort of used existing Py and C++ libraries.
Yeah.
And he sort of used the RVs. This is robotics sort of visualizer. It sort of shows you how sort of robots would move in real life if they use these libraries. And here's a Mars. There is a talk. Yes, that's the talk. If you're interested, have a look. He later implemented it on a real robot, and it's really cool. Sort of the real robot sort of moves and sort of shows, pretending that it's on Mars. So then there was funding available, and there was a project that Strigzinger sort of participated. So from that point, from Luca implementing DDS, ROSiE sort of started living life separate from me. So now it lives, but I have very little connection with it. And from that point, I'm really sort of glad and happy, because it seems I completed my academic purpose, and that I created something that continues to live without me. And I'm really proud and really happy about that. So Strigzinger with ROSiE, they participated in a project, TargetX, and there were a couple of sort of things they wanted to resolve, and one of them is a distribution, so enabling robots communicating over wide area network. So here you can see, you can think of robots, for example, being in one location, hazard, maybe some lab, and a human sitting in another one, and maybe there are a few areas, hazard areas that robots work on, but you need to sort of monitor all those robots. So now you can do that remotely. Intermittent connectivity, that was another problem targeted here. So especially if we talk about wide area network, then it's becoming really typical that sort of connection comes and goes all the time, especially if we work with the sort of rural area. So that was addressed. Bandwidth limitations, again, very typical one. As soon as you sort of moving out of the office, connections come and go. They were targeting that, and security concerns, of course. So as soon as we talk about robots and them doing something, then immediately we need some kind of security in place. So the first two were solved by adding bridge and hub. So hub monitors like which nodes we need to keep in mind, and they're sort of tuning what sort of parameters we want to have there, what bandwidth, for example, we want them to have, and so on. So that's hub. And then bridge makes sure that we sort of send messages. And here comes with fragmentation. It's about intermittent connectivity. So for example, for one types of messages you want bigger bandwidth, and for another smaller one. So you can all tune that in the hub. So yeah, we talked about bandwidth control. There was fragmentation mechanisms. So DDS actually provides how to do it, and that's what is implemented. So in general, DDS is huge, and ROS itself, it uses only sort of subsection of it, and what at the moment is done for ROSiE, implemented as much as needed. So as we go, as more things are needed, they're getting written, and then added. And in the security concerns we address with TLS, but also with GRISP2, that Strigzinger are working on, and that's there is a hardware sort of sitting on the board, and they're using it for making sure that the security, hardware security in place there. Just to mention that all this code, it was developed as part of a European Union project. So there are repositories here and they're available. So if you're interested trying them, I think almost all of them were developed in mind, not sort of type to ROSiE and GRISP2, so they can be used separately with other hardware and other types of software. The message that sort of I got was that ROSiE opens door of robotics community, and that was really I think nicely phrased, in that those doors are really closed, And I think when we enter any community, like think of you deciding to change programming language in your company or any other company, right? It's almost impossible. And here we're talking about entering a community with sort of their standards, their understanding, their sort of thoughts and vision, and having this bridge that enables us bring functional programming into the community who is absolutely not interested in any type of programming. I think that's really, really nice. And what it brings together is this amazing things, amazing libraries and knowledge that has been sort of accumulated in the Erlang community with those robotic force and interest that we have in ROS. So future is more Erlang proposals. Then they're also interested in getting into vehicles and swarms of drones, which I think is really fascinating. And ROSiE becoming part of GRISP.io. That's this sort of a bit of information is bringing edge to the cloud and connecting them. And these are both languages, Elixir and Erlang. Right, so that's the end of my talk, introducing ROSiE and explaining ideas behind it. Just a couple of sort of adverts. Erlang workshop is going to be in Singapore this year. So deadline for submission is actually today. So it's a little bit late advertising the paper submission, but the community there and organizing community is really nice. And if you're thinking to submitting a paper about functional programming, your experience, anything, there are developers who will be able to, and academics who will be able to help you to write your paper. So there is a year, so do think about it. And as I said, it's Singapore. So if you happen to be to Singapore, if you want a reason to travel to Singapore, it's with ICFP at Splash. There's a really top functional programming academic conferences. So do think about it. If you happen to be in London, there is an Elixir meetup in London. That's the webpage. Erlang Solutions is organizing. An organizing committee. They're not the ones. We are not the ones organizing it. There's a community behind it, but we help with the place and everything. So, but the main point that it's an Elixir meetup and it's in London. If you happen to be in London, do pop. And thank you very much.
Well,